Let's look now at another very nice property of vectors, which has a geometric background but which can be generalized and extended in all kinds of other situations where the geometry of it gets lost. So let's start in 2D, and so let's pick two vectors, u of components u1 and u2, that's the red vector there, and v of the components v1 and v2, that's the blue vector. Now by definition, I'm going to define a new vector which I'm going to call u plus v, simply as the vector which has as first component the sum of the first components of u and v, and as second component the sum of the second components of u and v as well. It's pretty straightforward, pretty reasonable, okay? And again, probably you're already familiar with its geometric interpretation, although probably not with the one I'm going to show you first. Well, how do we interpret this thing? Remember, we're adding the components. So what we can think of is if we still start at the origin with our geometric representation of this new vector, what we're doing is think of it as we're starting from u, and then we're adding a little bit of v. So what we're doing is we're adding both the y component and the x component of v. And here I think you may want to look at it either way. You can think of this process as taking v and adding to it the components of u both horizontally and vertically. Let me show you again. What I can do is I can start from v, or I can start from u, and then I can start from v and add to it the first component of u that moves it horizontally, and then the second component of u that moves it vertically. And now I can look at this new vector that I've just obtained. Oh, by the way, notice that this second copy of v is another geometric representation of the same vector. It's the same vector we're dealing with, not another one. Okay, it's just a different representation of it. Now you can tell that the sum u plus v is obtained by this directed segment that still starts at the origin but ends at the tip of this new representation of v. Okay. So this is what I would call the triangle rule. So this is a geometrical rule to interpret what we mean by the sum of two vectors. Now there is another way to do that, and that's by saying, okay, why just move v? Let's move u as well, or to say it better, let's pick a second geometric representation of u. Now if we look at the two original representations of u and v and the two new ones that we have constructed, together they form a parallelogram, and u plus v ends up being the diagonal of this parallelogram. If we use this geometric approach to interpreting the sum of two vectors, then we call this the parallelogram rule, and it's probably the one that you're familiar with. It tends to be a little bit more common, more popular. I personally prefer the triangle rule. It's easier to draw and also makes more sense later on when we're going to add more vectors. By the way, you may want to look up in my written notes for what is the geometric representation when we add several vectors. It's much closer to triangle rule than parallelogram rule, believe me. Okay, now in 3D, the idea is the same. So we can add two vectors in 3D by simply adding the first two components, and then the second two components, and then the third two components. And so everything is just exactly the same algebraically, but as you can tell, drawing it's a little bit more of a problem. And you can start seeing already how the algebra ends up being a lot easier than geometry, and it's the one that we're going to follow much more closely.